Hello, in this video I'm going to go through a fairly standard dynamics question. So we've got a diagram there, so look at the diagram and then see what isn't in it when we go through the text. Two particles of masses 3 kilogram and 7 kilogram, that's both marked, connected by a light inextensible string passing over a smooth peg. So two of our assumptions there, which are key to our approach, but they're not explicitly going to be in our answer, but we never want to forget these things. 3 kilogram particle held at ground level, that's marked on. String above it is taut and vertical, another one of our assumptions. The 7 kilogram particle is at a height of 80 centimeters above the ground, so we've got that. So everything that's in here is in the diagram, so we don't really need any of that text anymore. 3 kilogram particle is then released from rest by forming two equations of motion, show that the magnitude of the acceleration is that. Right, okay, so we've got tension going up in both of those for each particle, and then we've got the weight coming down for each one. So we've got weight 1 and weight 2. And we know that they're 3G and 7G, but you know, it's quite saves me having to draw out the diagram again. We'll have A going up there, A going down there, because that's clearly the way they're going to move. And then we're going to come in and we're going to use Newton's second law, which in this case, because the masses aren't changing, means F equals ma. So for the 3 kilogram mass, we're going to have that T minus the weight, which is 3G, is going to be equal to 3A. For the 7 kilogram mass, we're going to have 7G minus T is equal to 7A. So we want to add these together to get a single equation, because that's going to eliminate T for us. So we're going to have that 4G is equal to 10A. So we've got the acceleration is 2/5 of G. I mean, you could go to the calculator, but we can say, well, if G was 9.81, which is, well, actually, I think they're using 9.8 in this one, then we're going to have 4 lots of 0.98. So that's 4 minus 0.08, which is 3.92 meters per second squared. So we don't really need the calculator for such a simple sum. So that's 5 marks there. Now we've got to find the speed of the 7 kilogram particle just before it hits the ground. Right, various approaches to this one. Suppose the quick one, because forces aren't changing, so we can use suvat. So if forces aren't changing, the acceleration isn't changing. So we could jump in and use v squared equals u squared plus 2as, because we've got a and u and s, and that'll give us v. So let's start off with that one then. So v squared is going to be equal to 2 times a, so that's 1.6, so 8 over 5, 2 times s, sorry, and then multiplied by a, which is 2 over 5g. So we've got 16 over 25. So that's going to give us that v is equal to 4/5 when you square root it, so it's quite handy though, giving us 2 squares, times the square root of g. So that's one way of doing it. You might want to do it from an energy point of view if you're going to go more physicist on this approach. You think what happens when the 7 kilograms has hit the ground? We've had a change of potential energy of 4g, because rather than having the 7 in the air, we've got the 3 in the air. So we've had, if we do an mgh, as in we've got a 4g has dropped down to the ground times the h. So we could say that 4g times h, so that's 4g times 4/5. That's our change in potential energy. There's got to be the change in kinetic energy. But of course, both of the particles are moving at v. So we'd have a half of m, so that would be the total mass, times v squared. So you can see this is giving us the same thing here, that we've got a 4 times a 4, and then we got a 5 times a 5 on the bottom. So it's exactly the same setup as we had before. So that is also going to give us 4 over 5 times the square root of g. So same approach, and it's not surprising that you're getting exactly the same numbers, because this Suvat equation is a statement of conservation of energy as we're moving between potential and kinetic. So yeah, same only different. It's a bit more maybe to hold in your mind doing the energy approach, because you've got to think, well, both of these masses have changed, but the fact that the 3 kilogram has gone up, more or less replaced, you swap position of the two masses, so the MGH becomes a bit easier because you've got a 4 kilogram swing on that. So yeah, that's given us the speed before it hits the ground. When the 7 kilogram particle hits the ground, the string becomes slack, and in the subsequent motion, the 3 kilogram particle does not hit the peg, right? So it's just going projectile on us. Find the maximum height of the 3 kilogram particle after the ground, above the ground. So for the last bit, so it's got this velocity here, so we can say that well, we can do our mgh is equal to a half mv squared bit. So the m's aren't going to matter, so we need to do a 2gh is v squared. So this extra height is going to be v squared over 2g, is what we're going to be pulling out of this, which is going to be equal to, well, v squared is 16 over 25, and then the g's will cancel then. So 8 over 25 is what we're what we're adding on there. That's our extra h. So 8 over 25 is an extra 32 centimeters. So 32 centimeters on top of the 80 centimeters that we already had. So the total height is going to be 32 plus 80 centimeters, so 1.12 meters. And again, we haven't had to go to a calculator for any of these. So yeah, it's quite satisfying when you can get a question that goes that way. And you'll see how conceptually we've approached this question. I mean, we could have spent more time looking through all of these assumptions that we've got in the question, but I've done that in quite a lot of the other questions, so I don't want to spend time on that in every video. But we've applied our description of changes in motion using Newton's second law. But we've got these conceptual ideas, this conservation of energy approach that we've used in one way of doing the second part of the question, but also in the final part of the question. We're not just jumping straight in and saying, oh yeah, Suvat, 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 where you start losing the connection with reality. So yeah, it's a great way of approaching these. Improve your math skills so you're not jumping to the calculator, and you're getting nicer answers which are more precise, where you're leaving these g's in all the time, and also thinking conceptually, bringing in these core ideas of physics that we've got conservation of energy. This is a closed system. It's a closed system because the peg is smooth and the string is inextensible. We've got no forces acting inside, stretching this string in, and we're not losing energy in stretching the string. We're not losing energy in passing the string over a rough peg. We're keeping the system closed, which means we can do this conservation of energy approach with nothing being lost sort of coming out of here, of the peg getting hot or anything like that. So keeping those concepts in there, reminding us why these assumptions are so important.